So this will be our first lecture in a 3-lecture series dealing with kinetics. And this is all from chapter 16 in the book. The title slide here is a good overview of what these plots would look like for different rate orders that we'll be talking about for reactions. So if you plot concentration versus the rate of a reaction, if that concentration is constant, or the rate, is constant at varying concentrations, we call that a zero order rate. And that's of reaction because it doesn't depend on concentration. If it's linear with increasing concentration, we call that first order. And if it increases exponentially, that is a second order, or sometimes even higher. In plots of concentration of your reagents versus time, for each would look like this. You know, you'd go down linearly if it was a zero order rate because the rate doesn't change. First order rate, you go down exponentially, and then second order even quicker still. Okay, so today we're going to be covering material from the first 3 sections of chapter 16. So kinetics deals with the rates of things happening. In this class, we're going to be concerned with the rates of reaction. So if we have a reaction on top here, it's shown as purple going to green. We start with all purple. You know, after a certain amount of time, we have, about 50-50. Okay, and then, wait the same amount of time again. Now we have even less purple. And then by a certain time, there's almost no purple left. If we look at a different reaction, blue going to yellow, in the same time frame, you see that now it reaches approximately 50-50. Not even here at the end, it hasn't even reached 50-50 yet. So this blue to yellow is a slower reaction because less blue is turning to yellow in a given amount of time. And kinetics is just a way of measuring this, measuring how fast reactions occur. The book gives this figure. It tries to show you that, different reactions can have much different time scales. Like something burning or explosion is something that happens very quickly. And then it gives you these kind of macroscopic things like fruit or vegetables growing, humans growing, the lifespan of a human. And I'm not really sure what this is trying to, this picture's trying to tell. Maybe evolution, how slow that occurs, or plants growing. I'm not really sure. But the take home is that their reactions can occur over a wide range of time scales. What are some factors that influence reaction rates? Well, if we're talking about chemicals, the particles of the chemical or the molecules have to collide in order to react. They don't just react when they're far apart. They have to touch each other. Right? So the higher the concentration of the reactants, the greater the reaction rate because the chances of them running into each other are greater. Okay, the physical state of the reactants also influences the rate. Substances have to mix, right? If they have to collide together, they have to mix in order for the particles to touch and collide. So things like solids, the two solids would have to touch each other, and then the reaction would only happen on the faces that are touching, right? So things like a liquid or a gas that can easily mix together will have much faster rates typically. And finally, the higher the temperature, the greater the reaction rate. And this is because temperatures, at higher temperatures, the particles move around more, they can hit each other more, and the fact that at higher temperatures, the molecules will have more energy to collide, and then it's an activation energy that they can overcome. So We'll talk about this in a few slides, but sometimes particles hit and don't react, and because they just don't have enough energy to. So raising the temperature would increase that. This figure here shows the effective surface area on reaction rate. Both of these are steel trying to burn in O2. You can see that the nail, it's glowing, right? So something's happening, but it's only on that surface. But if you use the same mass of steel wool that has the steel in more shreds and more surface area available, it'll actually burst into flames. Right, so this is what we were alluding to with temperature. You need a sufficient energy for a reaction to occur. So in this case, our reaction is ozone plus NO goes to O2 and NO2. So ozone and NO have to bump into each other with a sufficient amount of energy. Okay, and when they do that, then they can produce a product. But if the energy when they collide is too low, they just simply bounce off of each other. Right? So raising the temperature raises the energy of the particles, the molecules in the mixture, and gives them a better chance of creating a reaction. So how do we express this rate of reaction? Well, the rate of the reaction is going to be measured in terms of the changes in concentrations of the reactants or the products per unit time. So our units are going to be a concentration per time. Okay, so if we look at a generic general reaction, A going to B, okay, if we want to measure the concentration of A at certain times, let's just say time 1 and time 2, then we can get an idea of how much it's changing. Okay, so the rate, again, is a change in concentration. In this case, we're concerned with A, over a change in time. So our change in concentration of A would just be A2 minus A1, those concentrations. Right? Remember, a change or a delta value is always going to be final minus initial condition. Okay, so A2 minus A1. And time, change in time, is going to be T2 over T1. And then we can write that as delta A, so the change, that delta stands for the change in concentration of A, over the change in time, so delta T. As we've mentioned before, but just to remind ourselves, those square brackets indicate a concentration. That's in moles per liter, molar. Okay. A negative sign is going to be used in this case, even though it's not shown up there, because the concentration of A is decreasing, right? A is a reactant, and it would be decreasing because this reaction is going forward. This gives a rate, a positive value. And that is shown here. Okay, so the negative sign is shown. So you'd have a higher concentration of A at 1, a lower concentration of A of 2, so this would also be negative, so this negative would cancel it out, and that's why the rate itself is positive. Okay, 3 types of reaction rates for the reaction of O3 and C2H4. Okay, so we have ethane and ozone reacting to form this species, C2H4O, plus oxygen. So if you look at the following black line, right, this black line shows the rate, or excuse me, the concentration of ozone at certain points, okay? So we're following it at different time points, and the time points are listed here. And you see that it's not a linear line, it's sort of sloping down. So we can measure the rate, the change per time different ways. So one of those is just taking the first point and the last point. So that would be A, right? And if we looked at A here, our rate would be given by this, 3.5 times 10 to the minus 7th. Well, we could also do like B here, we're measuring it from the first point to the second point, okay? And that gives us a much higher rate, or about 2 times as high as the rate measuring it from the first point to the last point. So this just shows that when we measure a rate, sometimes it's dependent on the time points we're using. And typically when you study rates, like in biochemistry, when you're studying enzyme rates, you typically want to try to compare initial rates, trying to get as close to this initial rate here, which would be E, as you can, just because rates do tend to slow down. As long as you're measuring the rate the same way between different samples, they can be compared. All right. We can also plot this out as concentrations of reactants and products versus time. So if we look at our reactants, they start at a higher concentration. In this case, this is for C2H4. And over time, it decreases. And you see it decreases pretty quickly at first, and then it'll slow down. With oxygen, right, it starts at 0. It's a product. And it'll raise pretty quickly initially, and then that rate starts to slow down. And as we learned in chapter 17, right, these eventually will go to flat lines, and that's a case where we've reached equilibrium. Right, so we can write rates here for the change in both. So we'd have rate equals negative delta CH2H4 over time, and that equals delta O3 over delta T. So the rate, and I believe that negative there is an error in the slides. There's lots of errors in the book slides for chapter 16, by the way. Because the rate of increase of O3 is equal to the rate of decrease of C2H4. So they should be equal and opposite signs. And if we look here, now we have a little bit different stoichiometry, right? Because we have H2 falling off. It's a reactant. The stoichiometry is now 2HI, so HI is increasing twice as fast as H2 decreases. So the rate of change of H2 over time is equal to the rate of change of I2 over time, equals 1/2 the rate of HI over time, because there is this 2 there, right? So you have to take that into account. And we do that by saying 1 over that number in the balanced chemical equation in front of your rate of change of concentration. And we can write that another way if you instead of saying 1/2 HI, you can say 2 times either H2 or I2. So in general, for just a general reaction where you have A plus B going to C plus D, and these small letters are the coefficients in the balanced chemical equation, we can write rates as, for the reactants, okay, it's going to be negative 1 over A times delta A over delta T. That would be the rate for the change in concentration of A. That equals the rate of concentration for B, negative 1 over B, times change in concentration of B over change in time. Okay, those are equal and opposite to the products. So the products would be 1 over C delta C over delta T, right? And it's a positive value. There's no negative sign there now. And that equals the same for D, 1 over little d, multiplied by the change in concentration of D over the change in time. So that's just in general how we would write for any reaction the rates. So let's try a practice with this. We have a reaction of hydrogen gas with oxygen. Okay, and so this, one of the reasons why hydrogen gas is such a attractive fuel source is because you can burn it with oxygen and it just produces water. It's extremely clean. And actually storing and utilizing the hydrogen, liquid hydrogen, that's the real hard part. But the actual reaction of it, it's very, very clean, and it's actually gives off a lot of energy. So it's a very attractive fuel source. Okay, we need to express the rate in terms of changes in H2, O2, and H2O with time. And then for part 2, when O2 is decreasing at this rate, 0.23 moles per liter per second, at what rate is H2O increasing? So our reaction again, let's remind ourselves. We have 2H2 gas plus O2 gas going to 2H2O. So for part A, we need to write the rates. So the rate for H2 can be written as minus 1/2 times delta H2 over delta T. You can write that rate for oxygen as minus delta O2 over delta T, right? Because the coefficient for oxygen is a 1. And then finally, the rate of H2O is plus 1/2 times delta H2O over delta T. Right? H2O is a product. It's going to the rate. It'll be increasing over time. The reactants will be decreasing over time. That's why there's a negative out in front. Second part, we're trying to compare the rate of H2O, H2O with O2. And we're given that value of 0.23 moles per liter per second. And that equals the rate of change of O2 well, what does H2O, if we wanted to solve for the rate for H2O? Well, we know that the rate of change of O2 is equal to 1/2 the rate of change of H2O. So if we solve this for the rate of change of H2O, what we'd get is two times delta O2 over delta T. Right, and we know that value is should be negative, right? We're decreasing that amount, so the negatives will cancel, but we'd get 2 times that. So it's 0.46 moles per liter per second for H2O. And again, it's a positive value because we are increasing that concentration. It's a product, it's being produced. Okay, so finding these rates is one thing, but we tend to, in chemistry, like to determine what's known as a rate law. And this is for any general reaction. Here we have our generic reaction A plus B going to C plus D. For this reaction occurring at a fixed temperature, we can write a rate law as K, which is a rate constant, and this is little k, not to be confused with the big K, capital K, that is the equilibrium constant. Okay, they do come from the same place. Big K is dependent on little k's, but in kinetics, when we're talking about rates, we're using the little k. Okay. So rate is equal to little k times the concentration of our reactants reacting together. And then M and N are going to be determined. Usually we say these exponents come from the balanced chemical equation, but in kinetics, they don't. M and N have to be experimentally determined. Okay, so K again is the rate constant, which is specific for a given reaction at a given temperature. So it is temperature dependent. The exponents M and N are reaction orders. Okay, and so the title slide, how we're talking about the different orders of reaction, that's where they come from. Okay. And again, they have to be determined by experiment. Okay, the values of M and N are not really related in any way to the coefficients A and B. Okay, so can't stress that enough. Don't think that because there's a coefficient out here, the exponents have to be the same. They're not related. So a reaction has an individual order with respect to each reactant. Okay, so if we do a simple reaction, A going to products, if the rate doubles when the concentration of A doubles, then the rate depends on A to the first power. Okay, so that's what we call a first order reaction with respect to A. Okay, if the rate quadruples, goes up by 4 times when the concentration of A doubles, then the rate is depending on A to the second power, or squared. And so this is what we call a second order reaction with respect or in A. If the rate does not change when you double the concentration of A, this is what's termed a zero order reaction because it doesn't depend on that concentration at all. So that's what we term a zero order reaction. And how these plots, if you plotted the change of a reactant concentration A here versus time, right? Zero order would be linear, right? The concentration would decrease the same over time, and second order and first order would decrease faster and then start to slow down over time because you'd be losing concentration, so the rate would start to slow. How K affects it is shown here. The larger K, you just make these curves, these exponential curves would be greater. You'd start off faster and be more have more depth to this curve for a large K versus a small K. We can also plot a rate versus A concentration. So as you increase the concentration of A zero order reaction, the rate is going to stay constant. Not constant. For first order reaction in green here, the rate will increase linearly when you increase A concentration. Zero order, the rate stays constant as you increase A, and then a second order, the rate will go up sort of exponentially there as A is increased. And we can write these rate laws as shown here, right? zero order rate equals rate constant times concentration of A to the 0 power, right? A to the 0 power would just be 1, so it's really just dependent on that rate constant. First order, it'd be K to times A to the 1 power, right? So it'd just be K times A concentration. That's why it's linear. And then the second order, we have K times A to the second power. So A squared is what this curve looks like. So if we look at this reaction, now we have NO, 2NO plus 2H2 goes to N2 plus 2H2O. The rate law here, experimentally determined, is equal to K times NO to the second power times H2. Right, the reaction is second order with respect to NO, first order with respect to H2. And overall, we would call this third order, right? Because you have a second order plus a first order. So that would be third overall. So you add those together, right? Note that the reaction is in first order with respect to H2, even though H2 has a 2 here in the balanced chemical equation, right? Remember those, the order of the rate law does not depend on that at all, okay? So it's experimentally determined. So let's try a problem writing rate laws. Okay, so for each of the reactions, use the given rate law to determine the reaction order with respect to each reactant and the overall order. For the reaction in A, determine the factor by which the rate changes if the concentration of NO is tripled and the concentration of O2 is doubled. Okay, so here are our reactions. So we have NO, O2, and overall. So the rate law is given here. So NO, there's a 2 there, right? It's raised to the second power. So this is second order. You can also sometimes write that as that degree symbol. It kind of stands for, you can have it as an abbreviation for order, so second degree rate law. O2, now O2, there's O coefficient of a 1 there, so it's first order, or primary with respect to O2. So overall, that's just going to be 2 plus 1, which would be 3. So third order overall. Now for this one, we're asked what will happen with the rate if you have 3 times the concentration of NO and 2 times the concentration of O2. Well, if we put 3 times the concentration of NO, that'd be like 3 squared. So we have a factor of 9 increase from that. And if we increased O2 concentration by 2, that'd be 2 to the first power. So that'd just be an increase by a factor of 2. So if we did those together, that'd be 9 times 2, or 18. So doing tripling NO and doubling O2, we'd get an 18 times greater rate for this reaction. Okay, so you just plug those values into that rate law and multiply them together. Looking at the reaction in B, we have the rate law, K times CH3CHO to the 3/2 power. So this one we would say is 3/2 order, and it only depends on that concentration, so the overall reaction is also 3/2 order. So reaction orders can be fractions. We don't typically see that in this class, but in real life, they can be fractions. Okay, finally, we have the reaction in C, and the rate is equal to K times H2O2 concentration times I concentration. But you'll notice that there's also H plus, as a reactant. So in terms of H2O2, hydrogen peroxide, this is a first order reaction, right? Because there's a 1 there in the exponent. I2, and I guess I should put that in concentration terms. I2, I minus is going to be the same, first order. H plus, now, if we were asked, what is this reaction in terms of H plus? Well, it doesn't factor into this rate law. It doesn't show up, so it's a 0 order. So how do we determine reaction orders? We've said before these have to be determined experimentally. So how do you do that? If we have our generic reaction A plus 2B going to C plus D, we can write our rate law, what we know it's going to be, K times A to the M power times B to the N power, and now we have to find out what M and N are. So to determine those, you run a series of experiments where you change the concentration of one reactant while the other is kept constant, and you measure that effect on the rate in each case. And usually, again, you use the initial rate just to make it consistent. Okay. So here's our data. We have experiment 1 and 2. We have kept B, the concentration of B constant, and we see that A, the concentration of A, has doubled. So we've doubled the concentration of A, keeping B constant, and what did that do to the rate? It has doubled. Now if you compare, let's compare the first and third. That concentration of A has been kept constant. The concentration of B has doubled. And you see that the rate going from 1 to 3 has also doubled. And then the fourth experiment, we've doubled both of them. If you compare experiment 1 to experiment 4, you double both of them, and you get about 4 times the rate compared to experiment 1. So calculating those M and N values. So if you compare experiments 1 and 2, where B is kept constant. So again, 1 and 2, we're keeping B constant. Right, so you have the K's are going to be the same in both cases. The B's stay the same, so they cancel each other out. And you're just comparing rate 2 over rate 1, so the ratio. So K's cancel out, B's cancel out. What you're left with is concentration of A over concentration of A at point 2 at experiment 2 over concentration of A at experiment 1. And you can determine that M value from that ratio. So you plug in the rates, right? The rates were 3.5 times 10 to the negative 3 over 1.7 times 10 to the negative 3. So that was 2 equals 5 times 10 to the minus 2 over 2.5 times 10 to the minus 2, that would equal 2 as well, right, to the m power. So m in this case has to be 1. Okay, you do the same thing where a is kept constant and b is changed, and that was experiments 1 and 3. And the line, again, this is an error in the book slides, should be through a's, not b's. Right, you do that same thing for b, and you see again you have 2 equals 2 to the n power, so n has to equal 1. If we look at a different reaction now, we have O2 plus 2NO goes to 2NO2. So our first and second experiments, we are keeping concentration of NO constant. And now this concentration of O2 doubles, so we're getting 2x. And when we do that, you can see that the rate doubles. So you might be able to guess there that this is going to be first order with respect to O2. If we look at experiment 1 and 3 now, we keep O2 constant and NO is doubling. And when we double NO, now we're going to get 4 times the rate. Okay, so in this case, NO, that coefficient is going to be a 2. It's going to be second order. So M would be 1 in this case, and N equals 2. And the slides here kind of go through this math. So the first and second experiment, we're keeping NO constant. We look at the rates, the 2 rates of those experiments with respect to the concentrations of O2, right? We're just plugging these numbers in from the table, right? And again, we get 2 equals 2 to the m power, right? So m has to be 1. And if you do those numbers, you don't get exactly 2 with these numbers. You get 1.99. But in real world situations, right, you're never going to, it's not always going to be perfect. So you can see that it's very close to 2. So you would round up. And then, you know, if we did that same experiment there for experiments 1 and 3, you would see that the rate, if you put in the rate of experiment 3 divided by the rate of experiment 1, that would be something like 4. So your concentration would be doubling of NO, right? 1.3 times 10 to the minus 2 over 2.6, or it'd be 2.6 over 1.3, so that'd be doubling to the n power, so n has to equal 2 for that case. Okay. Right, sometimes the exponent isn't really easy to find by just looking at the table of these values. So in those cases, you solve for those coefficients using an equation in the form of a equals b to the m power. And you would use logs. So sometimes, you know, using a log of a over log of b would make it easier to find these values. Right. Reaction orders may be positive, they may be 0, they could actually be negative, and they can be fractions, so they can be lots of different things. Typically in this class, though, we're just going to be looking at positive values, and they're going to be integers. Or you know, whole numbers, 0, 1, 2, things like that. In this case, if we wanted to use logarithms to find the coefficient for the NO in that previous example, right? We get we can do it the way that we did it. You can take the ratio of the rate divided equals the ratio of the concentrations to the n power. So you'd get, in that case, 3.99 equals 2 to the n. So, right, you round that to 4, n equals 2. You could also do that, let's say, 3.99 and 2 were your ratios. You would take the log of those ratios. So the log of 3.99 divided by the log of 2 to find out what n equals. Okay. It's pretty easy if you, like a number like 3.99, we know that rounds to 4. But if it was something that was further off, 3.67, 4.28 or something like that, and your concentrations weren't exactly 2, it was something else. Doing the log version of this, it might be easier to actually get to an n value. Right. So again, this is second order with respect to NO, and the total rate law then is given by this, k times O2 to the first power times NO to the second power. So this is third order overall. It turns out you can actually, if you're given a rate constant, just by the units of that rate constant, you can determine what order the reaction, the overall order of the reaction. Okay, so for a 0 order reaction, the units of your rate constant have to be in moles per liter per second. Okay, so that's what the rate is going to be is going to be moles per liter, that's a concentration, per second. That would be in your rate, you're dividing by an amount of time, so per second. So your reaction rate, they're always going to be expressed in moles per liter per second. Okay, so for a 0 order reaction, that doesn't depend on concentration. So K has to have the same units as your rate. Okay. For a first order reaction, K is going to be 1 over seconds. Okay, so why is that? Well, for a first order reaction, you have rate equals K times a concentration. Okay, so concentration is going to be in moles per liter, right? And remember our rate, we always want our rate to be moles per liter per second. Okay, so if our concentration is moles per liter, K has to be per second to give those units. Okay. A second order reaction, now it has to be, K has to be liters per mole per second. And why is that? Well, it's because your second order rate law is going to have a moles per liter there squared. So you're going to have moles squared per liter squared. So those will cancel with one of those, and you'll be given moles per liter per second as your rate. Okay. So knowing these units of K is very helpful. So this is a flow chart of how you would determine rate laws for a given reaction, right? Typically, you plot a series of plots versus concentration versus time, and then you would calculate initial rates, compare the initial rates when you change certain concentrations and hold others constant to find the reaction orders. Then you substitute the initial rates in and the orders and concentrations into your rate to determine what your reaction constant is. And thus, after you do that, you have now completed the rate law. So let's try one last practice problem. Okay. We have this reaction, NO2 plus CO goes to NO plus CO2. And we're given the rate law. we need to use the following data to determine the individual and overall reaction orders m and n, and then m and n, m plus n for overall. And then we need to calculate the reaction constant, rate constant, using the data that we're given from the table. Okay, so our first part, if we look at experiments 1 and 2, so experiment 1 and 2, we're keeping CO concentration constant, and the NO concentration now goes up by 4 times, and our rate is going up by 4 times. So for NO2, we're going to be comparing rate 2 over rate 1, and that equals 0.08 divided by 0.005. And the concentrations were 0.4 divided by 0.1, so that's to the m power. And when you do those fractions, it's not 4, it was 16 times. Concentration was 4 times different to the m power. So then you just by inspection, you'd see, what does m have to be? M has to be 2. So this is going to be second order with respect to NO2. We can do the same thing for carbon monoxide. Okay, now we're comparing experiment 1 and 3. We're holding NO2 constant, and we're doubling carbon monoxide, but when we double that, we're getting the same rate. So you might guess this is a case where we have a 0 order, but let's just plug everything in. Rate 3 over rate 1. That's just going to be, that ratio is 1. They're the same. We set that equal to the concentration now of CO. How does that change? We're going from 0.1 to 0.2. So in this case, n has to equal 0. So our rate, now we can write our rate, it's going to be K times NO2 squared times CO to the 0, right? CO to the 0 is just 1, so we can write this as just rate constant times NO2 squared. So overall, it's second order. Right, so now we can use experimental data in the table to determine K. So it doesn't really matter which experiment you use for this. You can use either any of these 3 experiments, but let's just go with the values from experiment 1. Okay, so for the rate for experiment 1, that was 0.005 moles per liter per second. We know that equals K times the NO2 concentration, which was 0.1 moles per liter, squared. So we can solve for K. So just in general, if we solve for K, K is going to be equal to the rate over NO2 concentration squared. So that's 0.005 moles per liter per second divided by 0.1 moles per liter squared. Right, so when we square that value, let's just take this one step further just to look at what the units are doing. We would have 0.01 moles squared per liter squared. Pen is acting crazy. There we go, squared. Okay, so moles per liter on top will cancel out with 1 of the moles per liter on the bottom. So what we get out for our unit now, for K, we're going to have 0.5, and the units will be liters per mole times seconds. Okay. And you can see from that table, that is the units of a second order rate constant. So that's all we have for this lecture. We will pick it back up next time in lecture 16.